Okay, Assalamu alaikum shabab. In this recording, we are going to cover two important aspects for clutches and brakes, which are basically the energy considerations. A very little topic, which just shows you how the energy is calculated. There is an excessive energy being generated or dissipated, I mean, during the application of the clutch or the brake. And then we will basically take that energy, assuming that most of it will be converted into heat. So once that energy is converted into heat, then we will be more interested in knowing what is going to be the temperature for the brake and or the clutch, and would we have problems reaching to a maximum temperature? Because as you might know, the material which we used as a bed for the frictional material, regardless what it will always have, is it a metal base, an unmetal base, it will always have a limiting maximum temperature. So the last part, which is section 1610, is very simple one. It's basically some tables about the materials and their characteristics. So hopefully we can cover it within this recording, and with that we will basically finish the complete sections for this chapter 16. So when are the rotating member of a machine are caused to stop by means of a brake, the kinetic energy of that, of the rotational kinetic energy must be absorbed by the brake. And that energy appear in the brake in the form of heat. Now, the total energy dissipated during the clutching operation or a braking cycle is the energy E, which is equal to I1, I2 multiplied by omega 1, omega 2. I1 and I2 are the the inertias, and we know that omega 1 and omega 2 are basically the angular velocities. So the angular velocity 1 and angular velocity 2. So if we divide it by 2 multiplied by I1 plus I2, where, as I said here, I1 and I2 are the inertias, and omega 1 and 2 are the angular velocities. This is if you use US customary unit, then in order to convert that energy into some heat in PTU, then you need to divide this energy by 9,336. This is if this one is US customary unit. Okay. Now, so the question then, what is the temperature rise in the clutch or the brake assembly? Okay, it can be approximated by the classical expression, which says that delta T is basically equal to H, which is the energy or the heat, divided by the CP, which is the specific heat capacity, and it is in PTU. Look at the unit, PTU, pound mass, not pound force, by degrees Fahrenheit. And it says here that we can use 0.12 for steel or cast iron. Of course, this is CP, and then we have W. W is the mass of the clutch or the part. So it is basically, if it is a mass, then it is pound mass. Okay. Now, if we want to have this expression in SI unit, then you need to make sure that E here is in SI unit, okay? And then the temperature rise measured in degrees Celsius will be equal to CP, again, the heat capacity, which is, by the way, that 0.12 here is 500 joule per kilogram degrees Celsius for steel and cast iron, where M is basically the mass. We know in SI unit, the mass is measured in kilogram. Now, if an object is at initial temperature T1 in an environment, okay, of a temperature T infinity. So let's say there is something which has been elevated to temperature T1, and then the surrounding, which is like a heat sink, has a temperature T infinity. Then the Newton's cooling model is expressed as the difference here between the temperature, a given temperature, and T uh, uh, for the environment, T infinity, divided by the temperature of the part T1 at a time T. Okay, so basically, no, sorry, T is the temperature at a time T. T1 is the temperature of the part, and then T alpha, T infinity is the ambient temperature, which is equal to the exponent of minus HCR. Do you remember HCR? We talked about it in bearing chapter 12. And then we have the area multiplied by W, which is the weight, the mass in pound force, in pound mass, I mean. And then we have Cp multiplied by the T. So basically what is happening here is that if the part has a temperature T1 and the environment has a temperature T infinity, at any given period of time T, okay, so you put time T 0, 1, 2, 3, 4, 5, whether it's in minutes or in seconds, and you want to know what is the temperature of that part after that period passed, then you need to know. So basically, T is the temperature at time T, and it is in Fahrenheit, degrees Fahrenheit. T1 is the temperature of the part. T infinity is the temperature of the environment. And then HR is the overall coefficient of heat transfer, which is measured in PTU per inch square second degrees Fahrenheit. Area is the lateral area or the surface area, which is an inch square. W is the mass of the object in pound mass, and Cp is the specific heat measured in PTU, pound mass multiplied by degrees Fahrenheit. Now, why this is interesting? Huh? Why? Let me tell you why. Let's assume that you're driving your car, okay? Now, and then let's say you apply the brake. And then when you apply the brake, the heat dissipated when you apply the brake, okay, could get converted into an increase in the temperature on the frictional material. So let's assume that now the temperature of the frictional material is T1. Is that good? This is now at TA. At time TA, you push the brake, and then you were driving your car. So what happened? The expression says the Newton's cooling law. It's an exponential law. And then it says that the change of the temperature with time, as time passes, is in exponential fashion. So as you see, the temperature start to decrease in an exponential. This is not uh, second order or third order. This is exponential. But then at time TB, you push the brake again. And then shoot, the temperature now got to T2. Is that right? So this is now the new delta T. Because when you added the temperature, when you push the brake at time TP, there was an initial elevation of temperature here, and then you add to it. And then let's say you drive and then you start cooling. So you can imagine what happened if you drive and then push the brake and then go, and push the brake and then go, push the brake and go. So you have this staircase thing, right? It's like before it cools down, you push the brake and then you elevate it again. So the question then becomes more like, okay, then can I know what is the maximum temperature? Huh? Can I know how much would I lose? And then I gain and then I lose. So what is the story over here? So the heat dissipation capacity of disk brake has to be planned to avoid reaching the disk and the bad temperatures that are detrimental. Detrimental, ya shabab, is a word which means that is damaging. Yes? And of course, yani, we cannot plan what people are gonna do. So you can imagine that this become a really interesting problem, right? You don't know how many times people will push the brake before it cools down. So there are a lot of uncertainties, of course. So when a disc brake has a rhythm such that, such as discussed above, which is we discussed it before, then the rate of heat transfer is described by another Newton equation. Of course, Shabab, the word rhythm means you go up and down, you go up and down, down, up, down. And now, rhythm is more of a systematic repetition. But and we know that we can't get this from our client if we are a manufacturer for brakes, like for cars. But there are always ways to get around these things, uncertainty analysis and so on. So the heat loss become very important. We want to know how much are we losing, because we don't know when maybe you will push the brake before we dissipate too much heat. So the heat loss is equal to, as we know, is equal to HCR, which combines, if you recall, in chapter 12, we said that HCR combined both radiation and convection heat transfer together, multiplied by A, the area, multiplied by the difference in the temperature. This is the well-known heat transfer law. So here we elaborated more by expressing two constant HR, HC, and FV to help us dig more into the problem, multiplied by the area and then the temperature difference. The temperature difference, I don't think you have a problem with it. The area, I don't think you have a problem with it. So let's dig into what are those other constants. So H is the energy loss, or the rate of energy loss, which is BTU per second. It's a rate. It has to be per time, per unit time. HC is the overall coefficient of heat transfer, which is in BTU per inch square S degrees Fahrenheit. I assume in your book you have an SI unit, maybe, so you can please study this as well. So we have HR. What is HR? This is a new one. The HR is the radiation component of HCR. Yeah, and of course it is a radiative energy transfer constant, so it has the same unit. All of them have the same unit. So HC is the convection component, all right, and FV is the ventilation factor. So you can't ignore the fact that yes, it might look terrible for a designer how to deal with the heat dissipation in cars, especially when people are reckless or there are some condition where people has to apply the brake a lot, one after another. There is also air. You're driving your car outside and you have a forced kind of convection most of the time. Air is being blown by the movement of the car. So there is a factor, there has to be, it makes sense that there is a ventilation factor. Then we have the temperature of the disk, and T alpha is the ambient temperature. Okay. Now, so what happened over here is you will ask question in general without getting into too much details. These are just examples. You may have to use different curves for different application. But this HR and this HC can be obtained from these two curves. So all what you need to do is the temperature rise. How much is the temperature rise? Which is funny because you will probably not know it. Yeah, the temperature rise is somehow related to the convection, the velocity, this ventilation factor. So you will see that probably the problem is inherently iterative. Yeah, but let's assume that you know what is the temperature rise. So when you know the temperature rise, you should be able to find what is HC, okay, and what is HR. What is FV? What is FV? FV has another curve. So I just kept the same equation here, just to remind you that this one is actually the uh, ventilation factor. So how much is, if you know the forced ventilation velocity, you should be able right away to get that FV. Okay? If you know these factors, then you will know how much you are actually losing. So this is very important. Why important? Because now we can run after this maximum temperature. Ultimately, that's what we want. Okay, so the energy observed by the brake, okay, stopping a rotary inertia I in terms of the original and final angular velocities. So here we said that the inertia, okay, which is like I alpha. Do you remember that? So the inertia, we will call it I1. This is the beginning. And then I2 is equals to zero. So it's complete stop. So the inertia I2 is equals to zero. And if we go back to the equation, right? If we go back to the equation, which is the energy equation, substituting I as I1 and I2 by considering I2 equals to zero and I1 is equals to I, and keeping in mind that this is expressed as a heat in BTU, so this is the conversion factor here, we will get this energy. This is now the expression for the energy. Okay, considering that the machine was moving with an inertia, initial angular velocity, and then it stopped. Okay, now the temperature rise due to this single stop. So you push the brake, you stop the car. Now what happened after? Before everything cooled down, you may move and then you push the brake again. So we are ignoring this right now. So then it is equal to delta T. This is the same equation that we talked about before, which is E divided by WC. Yeah. Now, then to find the maximum temperature, or to transfer this E BTU in T seconds, in T 1 second, the expression become like this. We have a T minimum minus T infinity divided by T maximum minus T infinity, which is equal to exponent of minus beta T1. T1 is the time for the stop, for the first stop. So where the beta is this factor. This is the same as the one I showed you earlier from the Newton cooling law. So all what you need to do now is then to solve for T max. So T max will be equal to T infinity, multiplied by plus delta T divided by 1 minus the exponent of minus beta multiplied by T1. So this is for a single stop. And this is to find the T maximum to transfer E BTU, which is the amount of heat in T1 second, in this much of second. That's it. All right. So we'll have an example about this, and then hopefully it will become very clear to you. So we have here a caliper brake is used 24 times per hour to arrest a machine shaft from a speed of 250 revolution per minute to rest. From 250 to rest. The ventilation of the brake provide mean air speed of 25 feet per second. This is really good. This is going to help us find FV. The equivalent rotary inertia of the machine as seen from the brake shaft is how much? I is equals to 289 pound mass inch second. Okay? And then it says the disc is a steel with a density gamma of 0.282 pound mass per inch cube. That's the unit of density. A specific heat capacity, this is the steel disc, has a specific heat capacity of 0.108 BTU per pound mass Fahrenheit, degrees Fahrenheit. a diameter of 6 inches, a thickness of 1/4 of an inch. The pads are dried centered metal. We're going to talk about them in the last section. The lateral area of the brake surface is 50 inches square. We want to find the T maximum and the T minimum for the steady state operation if the ambient temperature T infinity is equal to 70 degrees Fahrenheit. Okay, all right. So what I'm gonna do, I'm gonna solve this with you here slowly, and then of course this is part of an example in the book, and you can always refer to it if you want to. Okay, I'm gonna show you the solution later. So what did we say? We said that this brake is being used um, 24 times per hour. Okay, so an hour has how many seconds? 60 seconds by 60 minutes. So we have the time T1. Oh, let me start with the black color maybe. So T1 is equal to how much? 3,600 seconds per hour divided by 24. So in 1 hour, there is 24 times the brake is being used. Okay. So which is equal to 150 seconds. So what we want here is that the time T1. So remember 24 times, we're assuming that there's brake is applied one time, we have 150 second, and then the brake is applied another time, 150 second, and then another time, 150 second, and so on. So, what are we going to do? We are going to start by assuming that T max minus T infinity is equal to 200 degrees Fahrenheit. This is an assumption. Very important. Why? We don't know it. I told you this in the beginning. We don't know it. So we need to assume it. Now, if we made that assumption, then if you recall, we have a curve which or a figure which will tell you that T max minus T alpha infinity, sorry. And then we have HR, we have HC. Is that correct? So now if we assume this equals to 200, we can find these two. So let me go and find them. So HR will be equal from the figure equals to 3.0 multiplied by 10 to the power minus 6. Remember, the number here are all 10 to the power minus 6. You will see this in the title of the axis. Okay, and what is the unit? It is BTU per inch square second degrees Fahrenheit. What is HC? HC is equal to 2.0 10 to the power minus 6, okay? 10 to the power minus 6, and then BTU per inch square second degrees Fahrenheit. All right? Now, we have been also told that the velocity of air is equal to 20, how much? 5 feet per second. We have a curve, I think it was like this. And if we know that this is 25 feet per second, we will get FV. So we go to that curve and we will find FV, which is equal to 4.8. And remember, this is for speed of 25 feet per second. Good. All right. So what we can do right now is we can find HCR, right? We can find HCR. HCR, which by the way, we said that it is basically equal to HR plus FV multiplied by HC. We have, it was HCR, and then we replace it with HR plus VFV HC. So if we do this, we know this, ya shabab, this is it. We know HC over there, and we know V, F, or FV. So how much would I get out of this? I will get 12.6 multiplied by 10 to the power minus 6, and then BTU divided by inch square dot second dot degrees Fahrenheit. All right, good. Now, what is ultimately, ya shabab, ultimately, what do we want to find? Ultimately, we want to use this expression. Let me show you. Maybe I should have written this before. We want to find T max, which is equal to T infinity plus delta T divided by 1 minus the exponent of minus beta T1. What is beta? Beta is equal to HCR multiplied by the area divided by WCP. So we have already determined this. We know the area. It was given. What was the area, Shabam? The Was it given to us? The area? Let me see. It was 50. Yes, the break has a surface area of 50 inch square. So, and CP was also given to us. In the question, we were told that the specific heat capacity is equal to 0.108 BTU per pound mass degrees Fahrenheit. So my next step is to find the mass. So in order to find the mass, ya shabab, what do we have? We have the density. Okay? So the mass will be equal to the density by the volume. So we know that density, it was given to us as gamma, and we need to multiply it by the volume. I'm going to write it like this. This is the volume. Let me make sure you don't get it confused. So density by volume. Okay, what is the density? It was given to us. The density was given as 0.282, okay, pound mass per inch cube. So all what I need to do is to multiply it by the volume. What is the volume? We have been given the diameter of the disk. It was 6 inches. So the area is equals to pi over 4d square. And then we have been given the thickness. The thickness, I'm going to call it h. So an area by the thickness is the volume. So what I'm going to get, I'm going to get 0.282 multiplied by pi over 4 multiplied by 6 square multiplied by 1 over 4. That's it. So if you do this, you will end up with 1.99 pound mass. Okay, that's really good. Now, let's get to the next is to find what is, remember, if you go back here, we still have struggle. So we found everything in beta. We found T1. We still need to find delta T. Yeah, we still need to find delta T. Now, to remind you, just go back, to remind you, we said that delta T is equal to E divided by WCP. That's what we said. So, in order to find delta T, I need to find E. So, What is E? If you recall, we just said that E in there, let me show you, E is equal to this in BTU. So I will write down this equation for you. E is equal to 1 over 2, and then I divided by 9336, and then we have omega 0 square minus omega f square. These are the initial and the final angular velocities. Now, what do we have here? We have this as 1 over 2, all right? So we have 1 over 2. I was given to us. If you look here, if you say the equivalent rotary inertia of the machine as seen from the brake shaft is 289, and it is in pound mass inch second. So this is I. Then we divide by 9336. And then I have to multiply by the velocity. Now it says here it was going with a speed of 250 revolution per minute to rest. So this one is 0, while this one is 250 revolution per minute. Now you remember, whenever we have RPM and we have unit of energy or whatever, we need to convert this into what, يا شباب? Radian per second. And that's why we have to multiply this by 2 by, that's 2 by, which is what? 1 revolution, divided by 60 second for 1 single minute. Okay? And then multiplying this by 250, and we have square. Don't forget the square. Okay? So how much is this? This is going to be 10.6 BTU. That's the energy. Okay? That's the energy. Now, when we calculated this W, we know that beta is equal to HCR multiplied by the area divided by WCP, but I didn't calculate it. So if you plug all the numbers, you will end up with 2.93 multiplied by 10 to the power minus 3, and this is per second. So its unit is per second. Okay? Now, we got almost everything. So we will go to delta T, and we will say that delta T now is equal to E. Let me write the equation again for you so you don't forget it. It's equal to E divided by WCP. So what do we have here? We have 10.6 divided by 1.99 multiplied by 0.10, the CP 108. And if you calculate this, you will end up with 49.3 degrees Fahrenheit. Okay. Now, what is T maximum? So T maximum, which is equal to T infinity, which is 70, okay, plus delta T. Delta T, we just calculated it, 49.3, divided by 1 minus the exponent of what? Minus beta multiplied by T1. Minus beta, it is a minus, and then beta equals to 2.93 multiplied by 10 to the power minus 3. And then if you recall from the beginning right here, what did we say? We said that T1 is equal to 150 second. So we will go here and multiply this by 150. And how much did we get? We got T maximum equals to 209 degrees Fahrenheit. Now, this is T maximum. T minimum will be equal to how much? T maximum minus delta T. So, because delta T is the temperature rise, so T minimum will be 209 minus the 49. So 49.3, which is equal to how much? Is 160 degrees Fahrenheit. That's a problem. Why? Because the temperature, okay, difference T maximum minus T infinity that we are predicting here is what? Is 209 minus 70, which is equal to 139 degrees Fahrenheit. This part. Now, you go back to the equation and look what we did. We started by assuming that T maximum minus T infinity is equals to 200, while what we got is 139. So what should we do? We should iterate. We should solve this again and again. Go and predict a T max, which is maybe around T max minus T infinity, maybe close to 139, like maybe 150, 140. And then keep iterating until your assumption here is the same as your calculation. Now, in the solution of this problem, it turns out that, of course, each time you change these, you have to change HR, you have to change HC, and you keep iterating. So what happened? If you iterate until you get a convergent solution, you will end up with T maximum, which is equal to 220, and T minimum, which is equal to 171, of course, degrees Fahrenheit. So this is why from the beginning I told you that this is an iterative problem. Okay. Now, uh, I really don't know how long we've been recording this, but I will spare another 5 minutes to go over some reading material just for the knowledge. This is very important. So, this is the solution for you in order to see it. So, what we are going to talk about in the next few slides is the last section of chapter 16, which is a frictional material. Now, a brake or a friction clutch, okay, should have the following lining material characteristic to a degree that is dependent on the severity of the surface. High reproducible friction coefficient. You don't want your material to wear out, and then while it wears out, the coefficient of friction changes, and then could, like, after half of the age of the brake pad, you end up not having a coefficient of friction. If you don't have no coefficient of friction, how are you gonna stop? So uh, and there are you know consideration of the environment, like moisture, ability to withstand high temperature, together with good thermal conductivity, diffusivity, okay, as well as high specific heat. You need to have resilience, you need to have resistance to wear, scoring, and uh, scaling. You need to have a compatibility with the environment as well as flexibility. You can just think about too many features that a frictional material should have. Now, in the book, they have listed types of different ways to make frictional material. One of them is the woven cutting lining. The other one is the woven. This is the material we talked about before, which is called the acib, acib, acibis, acibistos. Yes, uh, and we have also molded acibistos, and we have lining, which can contain fibers. We have similar one with are made like pads. We have sintered metals pad, cermet pads, and others. So each one is described on how do they made it, if they are used for heavy duty application or like a drum brake. So this is very interesting description and information about the types of braking material and how are they made, manufacturers, and what are they used for. Here we have some tables that, for example, this describe the area of a frictional material required for a given average braking power. So you have here duty cycle. Is it infrequent or heavy duty or intermediate? You have an emergency brake, elevator, crane, and winches. You have excavators. And here you have the type of the brake, which is like a drum brake. And this is the corresponding um, um, area per energy. Okay. So per power, I mean. Here we have a plate disc. So these are the value as well as a caliber disc brakes. Okay, so each type with their corresponding application and what are the expected area per power. We also have here the characteristic of frictional material for brake and clutches. And what you see here is all type of materials that we talked about, and then their coefficient of friction. This is very interesting. So at least you know what is this coefficient of friction for this material. What is the maximum pressure that can it take? What is the maximum instantaneous temperature, continuous temperature, and the maximum velocity? And where should these application this material are usually used? This is very very useful. So if you start from the end knowing your application, you can go backward and determine what is the expected velocity, the temperature. At least you have a bounded solution, huh? You don't say, oh, I can reach to whatever I want. And then we have here another table for the property of the lining, brake lining, like the compressive strength, the tensile strength, and this is the way of making. Okay, and what are the the mechanical property that you will obtain from these different manufacturing methods. Then we have here the friction material for clutch. This is the same story, except that the other one was for a brake. This is for a clutch. And again, you have the material, and then you have the friction, whether it is wet or dry. And you have the temperature, maximum temperature in Fahrenheit or degrees Celsius, as well as the maximum pressure. Okay, so this is for clutches. That's it. This is the end of the last part of section uh, or chapter 16. And thank you so much, Shabab. We'll see you later.